Hey everyone, how are we doing? It is Thursday. Oh my gosh, it's the last day of Haslam week. We're getting ready to get going right here. So we are going to do some chapter 8 probably. If you're in the chat, feel free to jump in. We're going to do some chapter 8. Do chapter 8 quiz, a few more of those. We've done a lot of them. Chapter 8 quiz is a pretty good one. Noel, good to see you. I think we're really close to getting Mubot back. I'm bringing in the big people today. Bringing in the heavy hitters, kind of narrowed down the Mubot problem. Hoping they would fix it, but I might need to make some executive decisions about Mubot. He's not a virus, he tells me. That's what he tells me, and I say, I've known you a while, Mubot. I've known you for about 4 or 5 years, so. Kind of trust you, Mubot. It's scary. You think you know your friends, and then Mubot starts acting up weird. Whatever questions you have, let's do them. Do some easy ones, do some tougher ones, and knock out some questions right here. Let's pull up I know he should be back next class. I think he'll be back next class. It's a bummer we gone like 3 classes without him, but it's just the way it rolls sometimes here. It's the way it rolls here at Stat 201. I miss him too a lot. Stat 201, Chapter 8, Quiz, a variable. Let's go check this question out. Here we go. A variable that is not part of the model but affects the way the variables in the model appear to be related is called a what? Now, what you don't want to do with these questions is you don't want to click the drop-down menu. Why? Because then you get tips. You want to figure this out without looking at the drop-down menu. And one of my favorite graphics of all time is ice cream sales and shark attacks. And someone's got a really cool image here. We're going to copy the image, bring it over here to Word. And this is the classic example that apparently sharks love ice cream, or when you get ice cream, you just get attacked by sharks. One of the two. Well, as ice cream sales increases, shark attack increases, and as shark attacks increase, ice cream sales increase. So it looks like there's a positive correlation to both of them because they both increase in the same direction. And with that, it's not that shark attacks, so we'll put shark attacks right there. Shark attacks cause ice cream sales. It's not that shark attacks cause you to get ice cream or ice cream causes you to get shark attacks. It's actually time of year. And with this right here, we run into an issue of a lurking variable. So what is a lurking variable? It's when you have something that is not X, so we could call shark attacks X, we could call ice cream Y, and then the Z variable right here, the Z variable. So I call it a Z variable, not everyone else does, but I like to say it's something outside the XY paradigm. I don't have any questions, just finishing up number 5. Nice, we'll do canvas content. Yeah, let's do canvas content in a little bit. That's a good one to do. And so if you look at this, we have X and Y, shark attacks and ice cream sales, and then you have time is a lurking variable. So I really like their answers. This one's probably one of my favorite ones because what you see here is you have explanatory, the X variable, the response, the Y variable of interest, and a lurking variable. So very clearly, a lurking variable is something outside the XY relationship where it's the X and the Y that come into play and actually interact with each other, but it's the Z in the background time of year that we don't really see. And you get this a lot of times in graphics, like people can graph shark attacks and ice cream sales such that it looks like, and here's one graphic of here, why is the response one of those answers? Why is which response? So this is if you don't see the lurking variable. So this is where we have shark attacks as X and ice cream sales as Y, and it looks like there's a linear, maybe a little bit of an outlier weird relationship. And this is where you look at X and Y and say, well, it looks like shark attacks and ice cream sales are related, but in the background, there's actually this time of year variable that is the real variable, the Z variable. So what would be the type, what would that type of answer be? Yeah, it's a lurking variable. Lurking variable is one of the options, and it's a lurking. When a variable that is not inside the model is the one that is controlling it, a variable not part of the model, we call it a lurking variable. And that's just a key memorization thing. So that's we can do a lot of these easy questions. If we see a short one, we'll do a short one. We've done a lot of the longer ones. So this one right here, we did this one yesterday. I'm gonna get this one right this time. We did it yesterday, we got it wrong. Today we're gonna get it right. We're gonna do easy questions to start. Nice and little, this is the warm-up workout. Chapter 8. They're usually good concept reviews. A concert production. There's a lot of them that say a concert production company. Sorry if you're looking at this one, it's not yours. I've got a lot concert production company. They start them all with that. So what we have right here is a model where people are trying to predict for an artist who doesn't do advanced sales. So if an artist doesn't do advanced sales, we would be making predictions down here at advanced sales equal to 0. So if an artist does no advanced sales, the model would be down here where advanced sales are equal to 0. And the linear model goes something like this. Oh, I missed it. Oh, here we go. Whoops. The linear model goes something like that. And this would be an extrapolation of the model because we do not have data outside of the bounds. And you can kind of lightly extrapolate, like a little light extrapolation into this area right here, to this area right here. And we call it extrapolation because you're outside the bounds of the X variable. This one's worded a little bit oddly because they want you to say that you shouldn't be extrapolating all the way back here because the model is just very unreliable the further you get away from the data. Extrapolation occurs when the model makes predictions. And what do we mean by model? The model is the line. So when the line makes predictions outside the bounds by which the data is contained within, this is the bounds of the data or the scope of the data. It's the scope of the X variable. And so now we take a look and we see what coincides with what we just talked about. So this prediction is far away from the rest of the points. That prediction down there at the very bottom where we'd be predicting is far away from the rest of the points used to find for the model. And they're trying to find, this is where I got tricked yesterday, they're trying to find total revenue. So we're trying to find total revenue. And this is where I got super tricked. Therefore, this extrapolation is not valid. I think we're going to go with that. This doesn't say, and I kind of agree with them now a little bit as I think about it, as long as I get it right this time. It's not that the model is not valid. Extrapolating this far is not valid. So we should get 100. There we go. Just got to double check and got to make sure you get that energy drink in the morning. Then you'll get it correct. So drink your energy, drink energy drinks within moderation. Not every day. Well, this thing's another quick one right here. Okay. This one's a correlation causation. I can already see from the question. And yeah, the correlation causation question. Why am I talking about that as we start this question? Correlation does not show causation. No matter what the value of correlation is, you can't show causation. Probably the easiest thing to understand, and Noel, here's a really good question. I wish Mubot was here to give points. What is the correlation between any 2 points when correlation can be found? What is the correlation between any 2 points if we can find correlation? Yeah, I'll explain causation. You got it. What is the correlation between any 2 points when correlation can be found? What is the correlation between any 2 points when correlation can be found? Not 0.5. What's the shortest distance between 2 points? What is the shortest distance between 2 points? A what? The shortest distance between 2 points is a line. So since the dots are directly on the line, as best I could draw, the correlation between any of these will be what or what? If calculable, what will be the correlation? It'll be one of 2 values if calculable. There are instances when not calculable, because there's no variation in the X or the Y data. The 2 instances where it's not calculable would be a graphic where it's straight up and then you can't calculate correlation, or a graphic where it's straight across. This would have a non-existent value of correlation. So the 2 values of correlation possible when there's 2 points that when we can calculate the variation explained or the relationship between the X and the Y is either going to be -1, +1, +1, +1, -1. So what we mean by causation is if somebody, let's say, eats a cheeseburger, in that moment, do they weigh more? Like if you eat a cheeseburger, I just really want a cheeseburger. If you eat that cheeseburger, do you weigh more? Like in just mathematically speaking, for this up here, it'll always be if you have 2 points, only 2 points, you must either have negative or +1 correlation where calculable. Does that make sense, Noel? If you have 2 points, it'll either be positive or -1 when correlation is calculable. And so if you eat a cheeseburger, because I just really want a cheeseburger, you will weigh more. That's the cheese. Ingesting the cheeseburger causes you to weigh more. But we run into problems in statistics because we can't really show causation with our models. We can't say, and that's where we got to watch out. One of my favorite examples to do in stats is one where it goes with height and weight. So I'll bring up that data set really quick just so we can talk about that. And this is why we don't talk about causation here. I'm loading up R really quickly. I'll have it up in 2 seconds. Okay. So we're going to bring up a regression. So this is the regression output that we've seen before. And let me revisualize the model over here. Here is the intercept value. Here is the coefficient of the slope, B1. Here is the p-value of the model. Here is the r-squared value. 36% of the variation in height is explained by the variation in weight. But you can't say if somebody weighs more, they will be taller, because it's just generally that people who do weigh more are generally taller. But it doesn't mean if you weigh more, you will be taller. It just means we expect you to be taller. The model predicts that people who weigh more are taller. But gaining weight will not just directly increase your height. There are facts of the world, like eating a cheeseburger in that moment, you do weigh more. I'm fine with that. I'll eat that cheeseburger. But what we have right here is we have to be very careful with the word causation. And that's what this question is getting into, is you don't want to get into the idea of causation when talking through this. The correlation between cell phone usage and life expectancy is very high. Should we buy cell phones to help people live longer? It's probably a lurking variable of wealth, that people who can buy cell phones also have money. And if you have money, you generally live longer. And if you have money, you generally buy more cell phones. So no. Let's say this. Oh, there we go. Cell phones are relatively easy for people who are wealthier to obtain. And those who are wealthier typically have higher life expectancies. Since there's a lurking variables model, cell phones should not be subsidized. That's kind of okay. Well, so a lurking variable is, lurking variables are something you don't see. I have another good example of a lurking variable here. And I can show you how a lurking variable works. This is exactly how lurking variables work. Let's take, for example, a model where we explain somebody's height. Let me do this, attach, survey 10, that way I get the autocomplete feature. Height explained by num body piercings. Okay, so now if you look at this model, you can see the negative relationship. That people who have more body piercings are shorter. Does that make sense? As in, for each additional body piercing, the model predicts that the person is 1.25 inches shorter. Not that they decrease in height by that, we just have a prediction that they are that much shorter. So for each additional body piercing, the model predicts that the height of an individual is 1.25 inches shorter due to the negative slope of the model over here. But think about this. We've got height, body piercings. What might be the lurking variable that's not in the model? Like, what variable might we not be including? What is a variable that's outside of this XY relationship that might be the reason people have height and have body piercings? So like, what could be a possible, because this is Y right here. Height is Y, X is body piercings. So what might be a variable outside of X and Y? And that's what a lurking variable is. Like, it's not in the model. That's Y, that's X. You don't see, the lurking variable is not here. We can put it in the model, but the lurking variable is not here. So what a lurking variable is, another variable not already talked about. And that's what a lurking variable is. It's not in the model. So you have to think of it. You have to be like, what could be the lurking variable? What could be the variable that is associated with height and body piercings? Any ideas? So you have to think, what would the variable be that would somehow explain height and body piercings? Like why people are a certain height, why people have body piercings. What variable might that be? Well, that's kind of an association with height, right? And so the third variable is a totally different variable, and maybe it's gender. Because maybe women a lot of times, and we're not saying all, like my wife doesn't have her ears pierced, so it's not all women have more piercings. It's not all women are shorter. It's that there's trends in the data that we generally see women are generally shorter. Women generally have more body piercings. So what we do is we add in gender to the model, and you can actually see the male-female lines right here, and then you can see a summary, and number of body piercings is not as statistically significant, and gender becomes a very significant variable in the model. You can also see a lot of the male data points over here, or that's the female data points, where they have more body piercings, and the male data points don't have as many. They're the red dots right there, and a lot of the red dots are probably stacked up. So the lurking variable is probably gender right there. Maybe if I did it with weight, if I do it with weight right here, I think then it becomes not significant. I remember this example. There we go. And there's weight being explained by number of body piercings. And if you add in gender, yeah, that's what I should do from now on. Because now number of body piercings isn't significant. And we went from a very sloped line to a flat line where the real differences right here are between males and females. So what it is, it's because gender explains weight a lot, and because gender also explains body piercings, it looks like body piercings explains weight. Does that make sense? Because gender explains body piercings and gender explains weight, it looks like weight is explained by body piercings. So the way to, and this is how we do research a lot of times. The way to figure out if something's a lurking variable, so this is a little higher up, this is a little more 320, good questions, is if you see something where there looks to be a relationship between the variable. Number of body piercings is statistically significant. If something is a lurking variable and you put it in the model, so if gender is a lurking variable and I put it in the model, watch what happens to the p-value right here. That p-value right here, and I'll show it on the screen at the same time, that p-value that was low up here goes to a high p-value because it's no longer significant. So now in this model, number of body piercings is not significant. It's actually gender male. And we have other ways to analyze that with like variance inflation factor, and we can look at that. So there's more ways to analyze this, but we can figure out if something's a lurking variable, and the way to figure it out is to put it in the model. And the classic example, once again, is things like ice cream sales and shark attacks, where shark attacks and ice cream sales look to be related, but it's actually time of the year that's the real variable. Correct, it became less significant. So p-values that are less significant are closer to 1 because they're more likely by random chance, what we're seeing, the observed result. And then the p-values that are low are more significant. So in this model, gender male is significant, where the number of body piercings is not significant. Also, we can look at things like the increase to the multiple r squared, things like that. There's a lot of good ways to look at it. So remember, a lurking variable is something outside the x and y relationship that when we include the lurking variable, it will explain the variation in the model. Yep, a lurking variable is not x, not y. There's other examples like life expectancy and, well, the cell phone usage, but it's probably wealth. The classic one right there. There's other ones too, like examples of lurking variables, like shark attacks, ice cream sales. Here we'll do this one, the Gallup poll. This one's semi-short. We'll do 2 more after this, and then we're going to go do Canvas content. 2 more than Canvas content. Thank you, Noel. Good questions. The Gallup poll, we need to move up back. The Gallup poll shows a clear pattern right here. For each one you increase x, why do you increase on average? Yeah, well, this one, would this be increase or decrease slope? So when we look at this model right here, would this be a increase or decrease? Decrease, yep. And you would have something like, if you wrote out the model, it'd be y hat equals b0 minus b1x. So the way to determine if it's increase or decrease is to look at the coefficient of b1 and if it's positive or negative. b1 being the slope coefficient, b0 being the intercept when x is equal to 0. And remember, when you say b1, you're saying for each 1 unit increase in x, I expect y to increase by b1 on average. Good morning, Braden. Ask questions. We're about to do Canvas content next. Do you notice in this model how it starts out kind of flat? And then about here, it goes down to a linear model. It's kind of very plot not thickening. We'd have to look at a residual plot to check that, though. But really, we see a flat model that goes into a linear model, and that's what they're going to get into with this question right here. So let's see. Is there a clear pattern? It's mostly flat, and then it goes down here. Then linear. I think that's right. That looks good right there. I can tell by the model, but we need to know how to... Yep. Tell by the number B1. Exactly, the coefficient of B1. This is a super strong association. Strength is how tight the data is. So if I draw two graphics, which of these is stronger, A or B? I love asking it this way because there's a clear answer to this. Which of these is stronger, A or B? Which of those is stronger, A or B? Don't worry about getting it wrong. Strength is tightness around form. Yep, definitely A. There's the strength of B. There's the strength of A. A is definitely stronger because it's how tight it is around the form. This A has a parabolic form. B has a linear form. They're tighter, exactly. So this one right here, if you draw the tightness around it, it's very tight around its form. It has a nonlinear form, but it's still tight around its nonlinear form. So I think they're being a little bit mean on this one, though. Yeah, B is moderate strong, still pretty strong. B was still moderate strong in this graphic I drew. B was still moderate strong. It's weaker than A, but it's moderate strong. It's not vague. I think they're going for... Oh, is it the association appears weaker before 1970 than after? I think that's what they're... That's just... Is the linear model appropriate? No. You could fit it after 1970 to 2020. I think we've done it... Wait. The percentage of decreased non-linearly. No. It didn't change much. There we go. Where the numbers started. That looks right. That looks right. Good. I was like, there's only two patterns. If you look at how I divided up the graphic, I divided it up into kind of 1970 and before, and then linearly down to just show only those parts. Come on. There we go. Oh, I wanted that line. There we go. And then we'll do a division line right there. So there's really just two patterns to it. Two more. Let's do two more here. We're doing some of the short ones. That's a long one. That's residual plots. This is kind of fun. Why not? Let's do it. One more after this, and then we're going to do Canvas content. I haven't done this one lately, so I'm like, why not? And they do their residual plot a bit different, so I don't love the residual plot. There's many ways to make residual plots. Preferably... So would this model up there have a negative or positive slope? Noel, good question to review. Sometimes it... Yeah, it can do that. Is this a positive or negative slope? And actually, this one tells you in two ways. Great job. And what you'll see right here is they tell you in two areas right here. So if we bring this over to a Word document, not so much, but there is now, oh, I thought you said because of, yep, you are correct. There is an outlier. And you see the model would go like this. And so that indicates negative slope there. And then this indicates negative slope there. And then if we were to turn this into a residual plot, the preferred method on when I make residual plots, because there are different ways to make them, but my favorite residual plot is take the model, take the line, make it flat, and you can tell super quickly that that outlier has a what residual. What do you think I'm looking for there? That outlier has a what residual? I didn't do that line perfectly, but close enough. Has a very, very what residual? Positive, exactly. It's way above the line. And my line should have been a little more through the data. I went a little high through the data, but you can see the residual plot right there. You can tell the very positive residual. They did theirs a tiny bit different, but you can still see the positive residual down there. They just kind of have it reversed. And so are the conditions met? Nah, it's straight enough. It's just a huge outlier. So really that huge outlier when you look at it. So no. Do they not mention the outlier? The residual plot contains clumps. I don't see the clumps. The residual plot has much more variation for large predicted values. No, it's kind of the same throughout. They're talking about the plot thickening. So I don't see it. The residual plot shows nonlinearity. Nope. The residual plot is reasonably scattered with no evidence of nonlinearity. So it appears they're just asking about the line, which they should have asked about that outlier. which has a residual of about 20 or something. Is there an outlier? Yeah, there is. What data value is unusual? Select the correct choice. Its X value is about 7.8. You can zoom in right here and you go to the axis and you just trace down. It's about 7.8-ish. If you're wondering how we're doing that, just to show visually, we go right here and you want to take and plot about halfway, and that'd be 7.5. And then it might be 7.7 or 7.8. What is that is the residual plot. This is, if you, and you'll always see this right here, how to know it's a residual plot is right here on the graphic. It'll say residual. So you can tell the value of this, it's about 21 above because it has a positive residual of 21. So it has a residual of about 21. So that's how far above the line it is. So if we go back here and look at our previous drawing, this is about 21 above that line. Does that make sense what the pink graphic is showing us? The pink graphic is showing us that that's about 21 above because you can just go here on a residual plot, and a residual plot tells you the actual distance, and I prefer to draw them by making the line flat. They just did a slightly different way of doing it, but you can still tell that that's the residual. So it occurs at about 7.8. An outlier occurs of X of 7.8. The outlier has an unusually high value. I wish they asked what is its residual. Interpret the R squared. R squared is 63.6% of the variation in life expectancy, because that's the Y variable, is explained for, which means accounted by, for the regression on the X variable fertility, birth rate, which is fertility. I don't love the way they did that. I would say 63.6% of the variation in life expectancy is explained by the variation in birth rate. A little bit different, very similar. If government leaders want to increase life expectancy, should they encourage women to have fewer children? No, correlation is not causation. Although there is an association, there is no reason to expect causality. That answers it for me right here. Lurking variables are likely to affect both of those. Should get 100. We did get 100. That was a pretty good one. Pretty good review on lurking variables. This is one of the better questions. R squared, lurking variables, lots going on in there. Residual plots, all that good stuff. So good question. One more and then Canvas content. We'll knock out some Canvas content. If you got a question, let us know. We're just here working them. We haven't done the cyclist one in a long time. Why not? We were doing easy ones and we went to harder ones. Cyclist one throws people for a loop. They say, how do I do that cyclist question? I say, I got it. I got a video on it. Chapter 8 quiz. 100 years ago. You got to be like, 100 years ago. Okay. So this one is a jump question, so we need to use jump. If you don't use jump, you're going to have a bad time. We're going to click the box to open the data and then copy it using copy to clipboard. When you go to copy to clipboard, make sure to hit Command-C or Control-C to copy the data. Now, when you go inside of jump, you'll open up jump. Close out. If you have the window saying like tip of the day, just close that tip of the day. There'll be a little checkbox down there. Hit don't show tip of the day and then X out of that. I don't have it open. You might just, I don't use it, so just let it go. And now I'm going to hit File, New Data Table, which can be done via Control-N. For the data analytics projects, we just have to explain the slope, the intercept, and the R squared, and also the statistical significance. Slope, intercept, R squared, and statistical significance. Make sure to check the rubric. Make sure to get those points. Good questions, Noel. And now we're going to hit Edit, Paste with column names. This is one of those areas that if you make a mistake here, everything goes sideways. Let's make sure it looks correct. And this does look correct. The reason it looks correct is we know that year should be quantitative. Average speed should be quantitative. So we know those things right there. If you pasted without column names, it'll look the following way and be categorical, categorical, categorical. Look at the difference of quantitative, blue, versus categorical. Winner is categorical because that's a name. So we are going to make a regression model explaining the average speed based on the year over here. Let me make sure we're not subtracting. Okay, it doesn't look like we're subtracting, so we're good to go on that. To make the regression model, we're going to go to Analyze, Fit Y by X. This is the bivariate scatterplot creator for two quantitative variables. And here we are. Let's go in here and say year is the X variable. Does what year it is explain the average speed of the cyclist? And here we go. Click OK. Now you can see we got this weirdness right here and a gap during the wars. we can already go and figure out the answer to the first question because it just wants to tell where the plot is. Notice that there's not a drop here at the end. This looks about right. There's not a drop here at the end, and there's not a drop. So it's only the one without the drop. So that's easy enough. Describe the relationship. Well, you've got the weirdness. There were no races, I believe, during these timeframes during the wars. And so that narrows it down to A or D. Once again, if you look inside of here, we can expand it further out. And you can see a gap in here between 1915 to 1918. You can also see a gap here, and you could even go and check the original data to see the gap right there between 1915 and 1918, and the gap right in here between 1940 to 1946. So that does confirm these parts of it. We just have to figure out the next one. The slope is positive, and I'm going to say with a moderate amount of scatter. Scatter is the distance in the x or distance in the y. It's the vertical spread. It's not really that scattered when you look at it, as in that's not a large amount. We've seen plots that are like, so this one is really not that crazy. That is maybe the harder part of it. We should notice the gaps and stuff. We have to find the linear model. What value in notation goes right there? We wrote it out earlier. What is the notation value? I'll pause for a moment. See if you know it. It's y hat equals something plus something times x. What value would go right here? And we can go and find that value by going to the red arrow and going to fit line. The red arrow right here and going to fit line, and we get the values. There's the values right there. So we'll just call this AVG speed. What is that value in notation? What is that value right there in notation? This is known as the what? B0. That is the y-intercept. So the y-intercept needs to go to 2 decimal places, and that'll go to 90. And the y-intercept is negative. That would be at year 0. So that's not really interpretable. It's at year 0, the expected speed of the Tour de France cyclist. That's kind of a bit ridiculous. I don't think we go to year 0. And it's at 2 decimals. So I think this is going to go to 2 decimals right there. It was 0.143. Positive slope. Always check your slope is positive or negative. Are the conditions met? QQ straight enough. No outliers. Plot doesn't thicken. What do you think would be the issue with this plot right here, if anything? QQ straight enough, no outliers, plot doesn't thicken. The one issue we might have with it would be what? Of QQ straight enough, no outliers, plot doesn't thicken. To review the conditions again, QQ means both variables have to be quantitative. Well, we literally have a scatter plot. Technically, we have a time plot with special case scatter plots, so we're good on that. Straight enough, no outliers, plot doesn't thicken. What would be the issue here? So you have to think the 4 conditions are QQ, straight enough, no outliers, plot doesn't thicken, and this is to do a valid regression. So are there issues with any of the others? You can't do regression if you don't have 2 quantitative variables. So what are your thoughts on... You can check the other ones. I'll start doing drawings to check the other ones. The plot is pretty consistent throughout, and that's what I just did in pink right there. So what looks to be the biggest issue here? So, not outliers. Now, the yellows, I don't think those are really outliers. They're so minor. They're not really far away. The biggest outliers are rather tiny. Do you see the purple? Do you see the purple? What's the purple showing you? So the orange means we have 2 quantitative variables, QQ. The purple shows you what? Like when I drew on this right here, the purple's trying to illustrate the problem probably with what? Or I could have drawn the purple, not straight enough exactly. I could have done the purple the following way to try to illustrate that issue. Maybe like that. To try to illustrate, if we put a straight line through the data, there's data that deviates. So trying to show the deviations from the line right here, maybe do something like this, where the straight line doesn't go through the center of that data. So the problem is there's an issue at the early part that it's not straight enough. The model would have to bend through it. So you can see it right there. Like it's mostly linear, little non-linearity at the end. It kind of levels out. So maybe at the end too. I don't think they mentioned that. Are the conditions met? I think this is good right here. The relationship is not straight enough in the early part of the 20th century to fit a regression line. Let's check that. Yeah. Oof, oof. Yeah, it's a issue-y. It's problematic. It's a bit of a problem. It's a bit of a problem. Okay, let's do that canvas content. Okay. Why is my Outlook acting up? I don't like that. You're welcome, Noel. Thank you. I just hit 2 songs at once. My Outlook's acting up. Okay. I'm like not logging into email properly. I'm like, what's going on? Am I logged out of stuff? Oh, why is the world so weird? Oh, don't. I hit caps lock. Oh. My like email's acting up. Do a security's acting up. What is going on? Okay, I'm in. I'm in. Is Outlook? I feel like Outlook's acting weird this morning. Yeah, I know. Sometimes things log out, they act up. I'm gonna close down my email and say, you do you, email. You do you. You do you. That's what we say to that. Is Canvas acting weird? I don't know. Let's go over here to Canvas content. Canvas content. Canvas content. Tomorrow. Oh yeah, we don't got office hours tomorrow, so hey. 41. Chapter 8 quiz. Okay, let's take a look at it. Here we go. Okay, so the first question asks us, if we know the value of r squared, how do we find correlation? So let's take, for example, the following data. Let's go to Pokemon. Pokemon doesn't have a data set that works for it. Let's go to Kentucky Derby data. And let's go right here. And let's find the r squared. Oh, of course. Well, that's the... Oh, wait, it's not Kentucky Derby. Wait a minute. No way. That's the... Okay, that's that data. It's not Kentucky Derby. Movie rankings. They're like opening other... Why's I gotta do that? I'm trying to find a data set I want to work with here. And I'll have a data set. Trip Hammer Road. Spotify. Man, the data sets. Sure. Let's see this. Popularity year. Let's change year to quantitative. Analyze X. Does year explain the popularity? It's probably gonna be random. Ooh. Okay. Well, the r squared's so tiny, it's ridiculous. I don't want to give you an r squared that's a huge decimal. That's a pain in and of itself. Okay, so wind speed. Come on, wind speed. Okay, good. Okay, we got something. We got some data we can work with. Wow, that's a lot of data. Oh my gosh. Let's try this. Here we go. Jeez. Yes, that's what I want to see right there. That's the one I want. Okay. So what was the correlation for this graphic? I want it for an example right here. This is like a prime example. And so this will answer the question of what we're trying to do. And so this is what I want to show right here. What is the value of R? So if you look at this, you should be able to tell me the value of R. So what do you currently see at the bottom of the screen? So this is the example to learn how to do this problem and to memorize it. What do you see on the bottom of the screen, and how can we find r? What do we see at the bottom of the screen? I'll even drop hints right here. R squared. So what is the value of r? What is the value of r? So from r squared, find r. What is the value of r? I'm trying to figure it out in my head. Well, so what is it? Try to find the value of r. Try to find it. Put it in the chat. And it's a test question. It says find r. What is the value of r? What is the value of r? Try to find it. Usually we memorize things better by doing it. But here's the issue. If you take this value and you square root it. Oh, wait a minute, I didn't add a 0. If you square root it, there's a problem. The correlation is clearly what for this? The correlation is clearly what for this? So if you square root r, you need to check out its what? Because the correlation is clearly what? Negative. So it's negative 0.1339 right there. So when you go from r squared to r squared doesn't have a positive or negative value. You have to look if the correlation is positive or negative. So that goes back to what this question asked us. The question said to us, when you are finding, it says, if you know the value of r squared to find the correlation, what would it be? A, B, C, or D? If you know r squared, what would you do to find r? What do you think the answer is? A, B, C, or D? So what do you think the answer is here? From what we just did and what we just practiced, would it be A, B, C, or D? Oh, but remember, it's r squared already. So if you square r squared, you get r to the 4th. So remember, it is currently r squared. So since it's r squared currently, and good job, Noel, right here practicing. So since it's r squared currently and you want to find r, there you go. Take the square root of r squared to get r, and then check the direction. And that's what we were doing over here. I wanted to find an example of a negative correlation. And that's what we did right here to find the correlation. We took the square root of r squared, and then we looked at the direction. Hence why I highlighted this here. And that's the right answer there. And if you get this on the test, you are so lucky, because we just gave you the interpretation of the what. If you get this on the test, you're like, yes, because you just got the interpretation of the what on the test for you, where you can just plug in the values. Very clearly, this is the interpretation of the what. And you should know all these interpretations. Like, we don't usually interpret residuals, but this is an interpretation of the what. For each 1 unit increase in x, we expect y to increase/decrease. If it's negative, it'll decrease by b1 on average. So what would that be? That's the interpretation of the what? The slope. And then the residual is actual minus predicted. We don't usually interpret it. R squared is blank percent of the variation in y is blank by the variation in x. It's not correlation. Don't talk about correlation when doing R squared. Intercept is when x is equal to 0, we expect y to equal b0 on average. And the interpretation of the slope is for each 1 unit increase in x, we expect y to increase or decrease by b1 on average. Nice job. Great job, Noel. Here's output. So you're literally just looking at jump output. Once again, we don't have you use jump on the test, but you do look at jump output. And it says, what is r squared? You literally just look at the r squared value of 0.344, and it's 34% of the variation in y is explained by, we say associated here, but I like to say explained by the variation in x. So you just plug in y and x, y being finish time and x being age. The b1 value can be found right here for 2.43. That's the value of b1, also in the equation right there for 2.43. So b1 is the value of the slope of 2.43. And then the intercept, if there's time, yeah, gestation, yeah, you bet. You got it, Caroline. And then B0 is 156 right here. And that's just found right there in the output for the estimate of the intercept, and also up here for the intercept where B0 is at. Once again, make sure you know the equation, that the following equation, we'll zoom in on this here. I don't know why I make that noise. Y hat equals B0, the intercept, plus B1x right there, the predicted value of y. When you say residual, you're saying residual equals actual minus predicted, and the predicted comes from the model where the actuals are the dots. Like the predicted is that line and the actual is the dots, and the residual E is going to be the distance. This pen is way too big for the screen. So the residual is the distance. We've covered that a lot, but it's always good to just reinforce what we know. Didn't ask us anything about residuals. Oh, here's a residual. Wow. Wow. What's the answer to this question? Wow. Well, I'd love it if I got this on the test. What is the answer to this question? Man, I would love it if I got that question. I'd be like, yes. What is the answer to this? So it's asking, it says E is equal to 0. Observed is equal to, yep. because if the residual is 0, there's no difference. Then that's a residual of 0. So the predicted is the y hat value of 19.2. So if you write the formula, well, we figured it out because E equals actual minus predicted. I also write wrap actual minus predicted, and 0 equals 19.2 minus. If you don't know the predicted value, you'd have to sub in x, but notice how you can add x plus 0 equals 19.2. That's by doing algebra and bringing it over to the other side. And what plus 0 is 19.2? It's 19.2. And you can also just kind of theoretically work it that 19.2 minus 19.2 equals 0. They have no difference. And also theoretically, if the residual is 0, the actual and the predicted are equal to each other. Observed is just another name for the actual. So we have to use, I know, right? If I got that on the test, I'd be like, yes, because you're telling me they're equal. But remember the equations, we do give you those on the test, but know how to use them. This one right here is not so bad either. Can you solve it? I'll start showing the math. We'll do one more version of this, and then we're going to do the gestation question. Thank you, Caroline, so much for being here. So who can solve this one right here? You basically have to write the regression equation. I'll start writing it, see if you can solve it. Y hat equals B0 plus B1x. So can you solve it? I mean, that's, if you know that equation, you just plug in the numbers. So what's it going to be? How's it going to be? Do one more version after this. What is going to be the answer? What is the answer? So we're trying to find the predicted value. So this is the y hat. It says, what is the predicted value? And great job, Noel. Yeah, that's it. That's it. 11 plus, and then 3 times 10, 41. That's what it is, because it's 11 plus 30. There you go. That's it. It's 41. Just plug in the numbers. Nice and easy. Hopefully you got 100 on this. Hopefully I got 100. I got 100? 100! We'll do one more version. It might be a lot of the same. We'll do it a little bit quicker. If you know R squared, what you do, you square root it and check the direction. Take the square root, check the direction. Adding together all the residuals will sum to 0. That is a fact. The way the line works is when you draw a regression line, the regression line itself is going to go through the middle of the data. So if you had a bunch of points, I think someone else is named Brian. Hello? No, someone's around here named Brian. Hello, Brian. They're talking to each other down there. And you'll get positive and negative residuals. So summing up all the residuals will add to 0. It's just the way the math works out when you draw the line of best fit is what it mathematically does. It'll always add to 0. If a residual is positive, what's the answer? A, B, C, or D? A lot of people get this wrong. There's only 2 possible answers. If the residual is positive, what is larger? If a residual is positive, what is larger? And the answer is just to do this. And that's the answer. What am I talking about? So if a residual is positive, what is larger? If a residual is positive, what is larger? Correct. Great job. Because a residual being positive means the dot's up there, and that's the actual value. This is the predicted value where the line is at. And you would get this distance right here. So it could be something like 100, and this could be 60, and its residual would be positive 40, because it's 40 above the predicted. So it is the actual because it's above the line. So there you go. And then once again, plug in the numbers. 29, 6 times 3 is 18, plus 11, 29. If the correlation is 0.5, what is the R squared? So what is the R squared right here? If the correlation is 0.5, what is the R squared? Last one, then we do the gestation question. If the correlation is 0.5, what is the R squared? This one is difficult if you don't know that correlation is R. So this whole thing right here is R. That's what correlation stands for. So what is the R squared? So we're trying to find R squared, and we know. Yep, that's it. Yep. There you go. There you go, R squared. And so it mainly tests, do you know that correlation is R? And then do you know R squared is R squared? And that should do it. Let's do that gestation question. It's good. Good quiz. Because we wrote it. That's why I like it. Over to the main screen. Oh my God, sample source date. You're welcome. Yeah, and I hope you got 100. It's a good quiz, and not just because we wrote it. It's good, yeah. And it's just reviewing the concepts. You have to hear things multiple times, hence why I repeat things a lot. A lot. Let me put Canvas. I put chapter 8 quiz on that last one. Gestation. The D&E, you got it. You got it. Thank you so much, Kaylin, for being here. How's the question start? Oh, I think I found it. I found it. Is there any evidence? Is there any evidence? Let's check it out. For these data set, the correlation is 0.537. This is not very strong. It's moderate. Do you think the association would be stronger if humans were removed? So right here, humans are all the way over here. So do you think removing humans would make it stronger? Yes or no? Humans are that X over there. If we removed humans, do you think this would be stronger? So if humans, no mas. Oh yeah. That's a much stronger. Humans are pulling out the density ellipse. So humans are making the relationship weaker. And what do you think would happen? It would be stronger. And it's not easy. It might be easier to fit, but that's not how it works. It's that the slope would increase. The slope is getting pulled down by that. Is there justifiable reasons to remove humans? Yeah, if you want to limit it to only non-humans, sure. Here's a scatter plot for the regression analysis. Comment on the strength of the association. It's moderate to moderate strong, somewhere in that range. Perfect would be where all the points are on the line exactly. So it's not perfect because perfect means everything's accounted for. Weak is going to look more like a bigger scatter where the line does not have the points tied around it. So it's somewhere in between that. It's not perfect. It's not weak. It's moderate, strong. And so you want to have a good idea of how things look. Where the tighter it is, the stronger it is. Okay. Don't throw your pen, Brian. Interpret the slope of the model. Now, this is where we want to do it without it helping us. So what we want to do here is find the slope. And the slope of the model is given twice for some reason. Right here, they've got the R squared, and they've got the slope. And you can see right here the values of the R squared, the B0, and the B1. And so if we wrote the equation, it would be the predicted life expectancy is 89.3124 plus the slope coefficient of 12.86 times the life expectancy. So that's expected gestation. And so when we interpret the slope, we have to say for each additional year of life expectancy, we predict the gestation period to be longer by 12.86 days. For each 1 unit increase in X, we expect Y to increase by B1 on average. For each 1 unit increase in X, we expect Y to increase by B1 on average. So let's take a look at their answers. On average, for each additional increase in life expectancy, the gestation period is expected to increase by, and then we grab that slope coefficient of 12.86. That's the value of B1 right there because it's related to the X variable. A certain mammal has 24 years of its life expectancy. So we go back to the equation we wrote and we plug 24 in right here, and we hope we've carried enough decimals. We've got the number written over there, so we're just going to take 24 times it by the 12.86 0.8605, carry the decimals, add to it the slope coefficient of 89.3124, and we get about 400. We're going to copy that. Now, a check you can do, which is really great for this question, is it said a life expectancy of 24. So if you go over here and start drawing, I'm not going to lose that answer. What you should see is if you add a line to the data, and then you trace up at 24-ish, you should be about at 400. And maybe that is, maybe that's not. But it does look to be somewhat similar because remember, this is the line making predictions. We do have a bit of an outlier down there, but it looks to be close enough that yes, this prediction is accurate-ish for what we would expect. And it says round for the final answer, then round to 1 decimal place. So this whole thing looks to round up. I think that whole thing's rounding up. We'll hope we got it. We did get it. So once again, knowing that you're fitting the line to this data, where the line has the equation we wrote out earlier. It was something, well, you can see the values. It was like y hat equals 89 plus, and it was like 12x right here. And then you plug in the value of 24. So does that make sense right there, Caroline? Let me know if you have any questions. Hopefully I didn't do it too quick, but you need to write the equation y hat equals b0 plus b1x. And from there, you can plug in and solve. So really good work. I feel like you were right there. You had everything done except for D and E. So thank you for swinging by. I'm going to grab a snack, and then we'll start class. Mubot should be back next time. Next time Mubot will be back. But that sounds good. Yep, my office. Hope to get Mubot back. Be more than enough. Thank you so much. Okay. We're going to try to get Mubot back today. Bye for now, everyone. Bye.